Hey everyone. Alright, so let's go ahead and let's get into it. So some of you might have noticed that, okay, I don't have your exam scores posted on RenWeb yet, and that's because I haven't finished grading all of the exams yet. And so some of you have already gotten and I've already graded. I just haven't posted them yet because I'm still working on grading other ones. So I either got them late last night and I haven't had time to grade them yet, or the printer's being weird this morning and it's getting stuck trying to print so many of the pages. So don't worry about, oh, I can't see my score yet. It's okay. It should be posted later on today, so ask your parents to check back later today if you really want to know for it. But hopefully, whenever you see your scores later on today, you'll be happy with the scores. If not, and if you're a little bit concerned, we're going to talk about it on Monday whenever you come back. So just be happy right now to know your score and be like, okay, there's my score, and then I'll have questions about it potentially, possibly on Monday. We'll spend time going over it on Monday. Also keep in mind, what's due Monday? Right, remember it's the background paper, it's the final draft. How many copies of the background paper do I need? I need 2 copies, remember. So, for the background paper, I need the copy that doesn't have your name on the front of it. So I need the title page without your name for 1 copy. And then remember, it should have the paper plus the title page without your name. The other one should have a title page and the background paper with your name on it. I'm grading the one that has your name on it. I'm not grading the one that doesn't have your name on it, but I'm keeping it for you until the academic fair, which hopefully, we'll be able to have the academic fair later on this year. So don't forget, I need 2 copies. I emailed your parents about this already, but make sure you bring me 2 copies on Monday. Alright, so I'm going to give you some classwork because you had your exam yesterday, so there was no official homework, so I'm going to give you classwork today to help you kind of get started for it as we start our new section. I want you to read pages 113 through 116. So 113 through 116. Answer the questions on page 116, 1 through 4. Should only take you about 5 to 10 minutes, so like how we've been doing. So only about 5 to 10 minutes to go ahead and work on that. So page 113 through 116. Answer questions 1 through 4. Alright, assuming that you're still watching me at this point, and that means you've already paused the video and you've already worked on it, and so now you're coming back for it. So let's go ahead and let's go over it. Alright, what is chemistry? The organized study of composition and interactions of matter. Name the 5 principles of Dalton's atomic theory. Every element consists of tiny particles called atoms. All atoms of a particular element have the same properties. Different elements have different properties because their atoms are different. Atoms of different elements can combine in specific ways to form compounds, and chemical processes are the result of rearrangement, recombination, or separation of atoms. Alright, number 5. What is the name for a substance composed of one single type of atom? That is an element. And then what is the term for a substance composed of more than one type of atom linked together? That's a compound specifically. Alright, so let's go ahead and let's open up your textbooks now to page number 113. We are starting a whole new section, not just a whole new chapter, a whole new section. We're in unit 2 now. We're jumping gears and we're switching over into chemistry specifically. This is one of my favorite units because I know that I want to teach this really well, because not only do I teach it now, it'll help you get ready whenever I teach it to you next year in chemistry class. Some of you are 10th graders. You're going to be in chemistry next year. So you want to know this. Don't just think of, oh yeah, I'll have to know this eventually. No, you need to know it because next year you're taking chemistry. So this will help you out greatly. And then of course, everything in physical science is important because it's either for chemistry or for physics. So that's part of the reason why I know, okay, I have to teach this chapter. And not only do I really like it, but it's also where I know, okay, you're going to be using it in the very near future. Next year for some of you, 2 years if you're in 9th grade. So because of that, you want to make sure that you want to get this. Don't just think of, oh, it's just the chemistry stuff. No, it's important. So all physical science is good and all of it is useful, and you're going to use all of it at some point, but this is for chemistry in particular section. So it's a little bit different than the other sections we talked about. With equations, it kind of switches gears and it focuses more on chemistry and chemical formulas and how you solve them that way. So it's a little bit different than what we've been doing. Alright, chemistry and matter. Look at the quote at the top of the page. Chemistry is concerned with the study of the homogeneous or homogeneous, sometimes you guys have different pronunciations, of the uniform throughout substances or material through which all the objects of the universe are made up, with its transformation of the substances into each other, and with the phenomenon which accompany such transformations. So, what's he saying with Dmitri Mendeleev? Now, Mendeleev is how we technically say it. Now, he came up with our periodic table. I know you can't see it off to the side, but I have a periodic table in my room. And so he came up with how we organize the periodic table today. So that's where that quote's coming from. So he's talking about, what's he saying? Chemistry is concerned with the study of homogeneous or the uniform, how we see these patterns of substances or materials to which all objects of the universe are made up. And whenever you're having the transformation of one substance into another, you can have, they're seeing, okay, how does it work and what phenomenon or what happens whenever we do that. We can have one type of element change into another type of element. We call those nuclear reactions because you're changing the nucleus of the atom. So that's part of the reason where we get nuclear energy from. So you can have one whole element change into another whole element. Or you can have several elements combine and get different things. Like you might have heard of carbon. You might know what are some substances that carbon makes up. There are some substances that are made up of almost pure carbon, but because of how carbon's put together, they have different properties. Like for example, graphite, like in your pencil lead, that's made up of carbon. You can also have diamond, which is also made up of almost entirely carbon, and then also you have coal as well. So coal is also made up of carbon. So that's just a couple examples of how you can have one substance that can be combined or used in different ways to make different types of materials. So you have something like carbon that's used in a bunch of different properties, but it's being used or put together in different ways. Kind of how like whenever you build something out of Legos, I'm assuming most of you have played with Legos at some point in your life, or you at least know what Legos are. How do you take the building blocks, you hook them together, and you can build whole different structures or whole different buildings out of these individual Lego blocks. That's kind of like the same idea with chemistry. You have so many different types of blocks, but if you put them together different ways, you can get entirely new buildings or entirely new structures. So with chemistry, we're looking at compounds or how you can hook them together to make a new compound or a new type of substance. Alright, making up what chemistry is. Chemistry is the organized study of the composition and interactions of matter. There are 5 branches of chemistry. You had to learn these earlier in the year. Do you remember them still? Hopefully you remember organic chemistry, inorganic, physical chemistry, biochemistry, and analytical chemistry. What's the chemistry of living things? Biochemistry. And remember, if you're studying carbon, that's organic. If you're studying something else besides carbon, inorganic. Physical chemistry has to do with applying physics to chemistry. And then analytical chemistry means that you're analyzing something. So look and figure out how does it work, what are the parts for it. Alright. So make a note of those, the 5 branches of chemistry. They don't have them bold and italicized on this particular section, but it's just pointing out that, hey, these are the 5 branches again. So you should have learned them earlier in the year, so just pointing them out again, you have to know them again. Alright, so your book points out that people have been using history for a very long time. Normally whenever we think of chemistry, we think of it like this, with equations and mixing dangerous chemicals together and causing explosions. But we've been using chemistry for a long time. Your book talks about there are records of people using chemistry even before the flood. Now the Bible doesn't call them chemists, but the Bible talks about a man named Tubal-Cain that he was working with brass and iron. All right, so iron. If you look at the periodic table, the camera can't pick it up over here, but if you look at the periodic table, you would be able to find iron. Iron has the symbol Fe for it, and we'll talk about the reasons why later on. But it has the symbol Fe, so you can find iron or iron ore. You can't find brass as a pure element. If you look at the periodic table and look for the element brass, you can't find that. That's because brass is an alloy, or it's a mixture of 2 different or more elements together, metals in particular. So kind of like steel is made from mixing iron and carbon together, you can get steel. This is where sometimes students, they will bring up Minecraft. Now Minecraft is not a very educational game with the fact that they keep everything perfect, but the designers of Minecraft did actually do a lot of their research to make sure that they didn't make a lot of stuff match up. So because of that, you might think of, oh, in Minecraft you have to find iron before you make steel. Yep, and that's the same idea. You can take iron ore and you can purify it and mix it with other elements and make steel from it. Steel is a stronger version of iron. So, just make a note though that whenever he's talking about using brass, that's whenever he's taken one substance and he's converting it into that compound or brass. So it's a different type of metal that you don't find a pure substance of in the earth. Alright, your book points out as well that it looks like the ancient people of Iraq may have used electric batteries to plate jewelry. It looks like the Roman engineers, they used concrete to construct giant buildings and aqueducts. Japanese swordsmiths of the 1400s, they produced hardened steel through chemical processes, which again, you can't make just steel just by finding steel out in the earth. You have to actually make it and combine it with iron and carbon and other things, but kind of iron and carbon mainly. So that's part of the reason why people have been doing this for hundreds of years, in some cases thousands of years. They didn't call it chemistry. They didn't have that terminology for it. Some cases in the Middle Ages, they would call it alchemy. You hear that term thrown around for it, but it would be the idea of they are a metalsmith or a swordsmith or a blacksmith in a lot of cases. They are using these substances, they just don't call it chemistry. Your book points out each of these your book points out that throughout the centuries, apothecaries, so these would be someone, they have produced perfumes, ointments, and medicines by using chemicals from plants out in nature. So they would take different substances from nature and they would combine them together, and they knew that they could get a new substance. But they didn't know the chemistry over why it happened. It just does. And they weren't sure exactly what was going on with it, but they knew, okay, if I combine these two things together, this happens. Not sure why, but it does. So they were using chemistry, they just didn't have the proper names for it. So your book's pointing out though that a working knowledge of chemistry was they were using it, but it wasn't until the Reformation that whenever you started having people going back to the scriptures with that revival of learning, they actually started going back and saying, okay, what can we use now? How does this work necessarily? So trying to discover why do things work this way for it. So how can you have two materials combine and get a whole new substance? How does this work? Why does it work this way? Throughout the Middle Ages, the Roman Catholic Church didn't really like chemistry or alchemy. It was seen as kind of like wizardry or witchcraft. So let's come today, we associate alchemy with more of fantasy games and wizards and witches. Now, alchemy doesn't necessarily mean that, but just because the church viewed it like that in the Middle Ages, that's where a lot of that stereotype and stigmatism comes from. By 1800, though, the scientists had laid ground for a revolution in the science of chemistry, trying to figure out, okay, why do things work the way it is? They want to make the chemical knowledge useful, though, for the good of mankind, rather than just discovering it just to learn how does this work. They said, okay, we can take this now and we can use it to benefit man. We can help out other people. We can make better medicines. We can make better fertilizer. We can make better things if we know how to do it. So chemists started to share their information more, not just keeping it more a secret, but they wanted to share it with other chemists as well and figure out, okay, how can we build from each other's knowledge? All right, next page. All right, so your book points out chemistry affects every aspect of modern life. Your book gives you kind of like this list, which is on page 114 on the left side. So your book points out whether you shampoo your hair, put on cosmetics, brush your teeth, wear dyed clothing or clothing made from nylon or polyester, ride a car, pitch a tent, use a camera, a computer, or a flashlight, take medicine, read this book, you're using a product of chemical industry. Alright, so you might be thinking, well, how does chemistry affect everything? Whenever you're using shampoo in your hair, there is a reason as to how come soap attracts grease, because your hair makes sebum, that's a type of oil. So because of that, it attracts grease or pulls the grease out of your hair. There's a reason that soap works that way. Because of the chemical attractions between the soap molecule, water, and the grease in your hair. That's the reason why shampoo pulls the grease out, or whenever you brush your teeth, the reactions with the toothpaste helps cleans the plaque and the germs and other bacteria out of your mouth. Whenever you're wearing dyed clothing today, we use a lot of chemicals to dye our clothes today, and particularly if you have a lot of polyester, or if you have a nylon article of clothing. Nylon is kind of like silk. You probably don't wear a lot of nylon, like nylon stockings, but polyester, if you look at the tags of your shirt, you will realize a lot of your stuff is either made up of cotton, which that comes from a plant, or polyester. Polyester doesn't get as wrinkled as pure cotton does, and it's not as hot and inchy. So a lot of your shirts today are made up of polyester. Whenever you ride in a car, you're using the chemical reactions of gasoline in the engine to help power your car. Whenever you're pitching a tent, since your tent in a lot of cases is made up of a type of plastic, you're using a type of chemical substance like that, because plastic is not found naturally in the world, it's a man-made product. Use a camera, so chemical reactions. Now, whenever you're using a camera, it means like a photograph camera. So whenever you're using like an old disposable camera, that's a type of chemical reactions. And your cell phone, because your cell phone is digital, it's a little bit different, but there is electricity happening on the inside for it. So using a camera, a computer, or a flashlight, all those electrical charges, you have those electrical types of batteries. That's a type of chemistry. Whenever it's running on a battery, whenever you have the electrons are moving around on the inside, that's a type of chemistry. So again, your cell phone, your computer, camera in your cell phone, all of that works off using some type of chemistry. Or reading this book. So making paper today, a lot of the factories use a chemical process to make it to bleach the paper. And so the book is pointing out there's a lot of industries that use chemistry that you don't even think about. Alright, there's some other ones your book points out. Modern high-yield agriculture depends on chemistry to provide enough food for large urban populations. So in America, a lot of our people aren't necessarily farmers or raise food, but that's the reason why you can have one farmer grow enough food for his family and for other families around him. Because he uses fertilizer, he uses pesticides to keep insects away, and he's growing enough food for everyone. He might use special types of crop seeds, he might be using different agricultural methods in order to make sure that he gets the best type of plants for his land. So that's probably the reason why in America, you don't have to be a farmer to get food. Back in the olden days, way back in colonial time periods, you probably had to grow your own food or catch it yourself. Today, you don't have to worry about it. You go to the store, you can just buy your food that way. And it was probably grown in the United States or maybe somewhere else around the world. That's the reason why, though, not everyone has to be a farmer. You can buy food because the farmers we do have make enough for not only for their families but for other families in the United States as well. Now, your book points out, sometimes people, they say that chemicals are bad or always bad and natural substances are always good. That's not necessarily true. Now, you have to be careful of some chemicals like bleach. Okay, bleach is a useful chemical product, but it is dangerous. You get bleach on your skin, if you've ever done that, you know it hurts because bleach will basically burn you. If you drink bleach, it'll make you very sick. I'm not putting it mildly, don't do that. So, because of that type of chemical is a very strong chemical. So, because of that, you do have to be careful with them. But just because it's a chemical doesn't mean it's bad. Technically, everything in the world is made up of atoms, so everything is some type of chemical compound. So just saying something is a chemical doesn't mean it's bad, because everything in the world is made up of atoms, and all matter is made up of atoms. And since atoms can be used to make compounds, that's a type of chemical. So your book points out that sometimes people, whenever they talk about chemicals, they use it as a bad way, and they say that natural substances are good substances. But technically, that's in chemistry, everything's a compound. It depends on, are you talking about the type of pesticides or what type of strong chemicals are they using? So just to be aware for it as we're getting into it. But technically, everything in the world is made up of chemicals. Alright, so John Dalton's atomic theory. So make it over him. So this was the greatest discovery of modern chemistry, came in 1803 when John Dalton came up with his atomic theory. So make it over him. So John Dalton, I took the box at the top of the page and I basically condensed it down. So John Dalton's atomic theory, so I tried to simplify it. So if you want to go off my chart, that's fine. If you want to go off your chart, that's also fine. So look at the top of the page. So he said that every element consists of tiny particles called atoms. So what's he saying in this section is that, okay, all the pure elements, all the elements we can find out in nature, they're made up of these little bitty substances called atoms. Now remember, this is not the same thing as a cell. A cell is a living unit of a body or a living unit of a living organization, of a living organism. The atom can make up a single element. So we have 118 elements. That means we have 118 different types of atoms, if you want to think of it that way. Alright, all atoms of a particular element have the same properties. So it doesn't matter if I find oxygen in the air or way high up in the atmosphere. If I have oxygen, just regular oxygen, then it's still going to act the same. So all atoms of a particular element have the same properties. Or if I find gold in the ground or gold in the jewelry store, if both of them are pure gold, then they have the same properties. They're going to be a yellowish color, they're going to be shiny. Pure gold's really soft as a side note, so it's very malleable. So it doesn't matter where you find it. If you have pure gold, it doesn't matter if it came from the bottom of the sea, top of the mountain, in a jewelry store, laying in the desert, if you get really lucky and you just happen to find it. But it's the idea of, okay, its atoms are going to act the same. It doesn't matter where you find it at. Different elements have different properties because their atoms are different. We're going to talk more about the reason why for that, but yes, that's part of the reason why, since the atoms are different, the elements have different properties. Like, for example, what gas do your lungs need to breathe in for you to carry on life? Yep, oxygen. So, oxygen you breathe in. Technically, oxygen always has a buddy, so dioxygen in oxygen, you breathe out carbon dioxide. What if you were to just breathe in nitrogen? Now nitrogen's in the air, technically it's dinitrogen and dioxygen, but nitrogen's in the air. So if I have nitrogen in the air and I breathe it in, will I still get the air that I need if I'm just breathing through nitrogen over and over and over again? No, it's not the same thing, it doesn't act the same. Or if you breathe in helium, you might have done that at a birthday party where you get the helium balloons and you breathe that substance into your body. Okay, you're breathing in a gas, but can your body use it the same way as oxygen? No, it doesn't work right. That's probably the reason why your voice changes and gets really high whenever you use helium, because it messes with your vocal cords a little bit differently, but your lungs can't use that. It's there, and so it fills up your lungs, but you can't use it. That's why you'll start to get dizzy if you use it for too long, because you're about to pass out, because your body's telling you, I need oxygen, not helium. It's not the same thing, I need something else. So that's what I was talking about, different elements and different properties because their atoms are different. So an oxygen atom, I'll erase these two now, is different than a helium atom, and it doesn't work the same way. Alright, number 4, atoms of different elements can combine in specific ways to form a compound. We'll talk about what a compound is in a second. But I can have carbon monoxide and carbon dioxide. So, carbon monoxide, so it's a C and an O. You might know, okay, where does carbon monoxide come from? Not you. I guess maybe you. But it comes from combustion, like with your car engine. So the exhaust that comes out your car, that kind of weird smell, that's carbon monoxide. Carbon dioxide, that's what you breathe out with your lungs. So these are two different compounds and they react two different ways. So you might think, well, this one just has another O on it. Yeah, it does, but it makes it act entirely different. So atoms of different elements can combine in specific ways to form compounds. And then number 5, chemical processes are the result of the rearrangement, recombination, and separation of atoms. There's no way I could simplify that one, so I just had to just use that one as is. So chemical processes are the result of rearrangement, recombination, or separation of atoms. So I can take the 118 different elements that we know of and basically hook them together in different ways, like Legos, and I can build different compounds. Now some compounds are more dangerous than others, and some of them are more reactive or explosive than others. But you can combine them in different ways in order to get a new substance. So make a note of the 5 parts of Dalton's atomic theory. Alright, so going through some of these terms now. So your book tells you especially what some of these terms mean. I've been using them, but now your book's giving you your official definitions for them. John Dalton proposed that all matter consists of tiny particles called atoms. Make a note that atoms make up all matter, so make a note for that. So of substance, whether it's your bedroom, like your bed, or your table, or your TV, or your snack that you're eating now, or maybe later, all of that is made up of matter, and all matter is made up of atoms. So you have your matter that's broken up into smaller pieces. An atom is a small piece. So make a note, this is tiny particles, what you call atoms. He called them atoms based off the Greek word that means not cuttable. Technically, you can break an atom into pieces. We'll talk about how that works later on, but he didn't know that at the time, so it's okay. So, atoms. Now, he also suggested that atoms can combine in various ways to form different substances. Substances, he said, or elements are made up of one type of atom, like a chunk of gold, or silver, or copper. You can find those out in nature as a pure element. It's made up of one type of atom all throughout it. Or you can read them like oxygen. Oxygen is an element because it has one type of atom all throughout it. Some substances are composed of more than one type of atom linked together. So, I moved my chalk. There it is. Alright, so like for example, rust is made up of iron and oxygen together. So instead of having just regular iron and oxygen, you combine them together and to get iron. Typically, I think one of the common versions of iron, I believe, is this. Could be wrong, but I think that's a type of iron oxide for it. So, your book is pointing out that, okay, you can have different types of elements combined together to get a new substance. Or, like, you combine oxygen with carbon and get carbon dioxide. So your book's just pointing out that we call those compounds. These are substances composed of more than one type of atom hooked together. So they're a combination. They're not the same all throughout it. Alright, let's see. Kind of already talked through most of it. To make it a little what a molecule is a group of atoms linked together. So, like for example, I've been using oxygen. Oxygen typically likes to have a buddy to where oxygen will bond up and basically hold hands with another oxygen. Technically, it's a chemical bond, but if you want to think of it as holding hands, that's fine. So oxygen wants to bond up with another oxygen. Nitrogen wants to bond up with another nitrogen. So we call these molecules because it's two of them and they're staying together, but they're the same type of atom. So these are both elements because you can find them as a pure form out in nature. So they just make up one type of atom, but they can also be hooked together and basically buddy up or pair up. So we call them molecules specifically. It has something like this, like water. Water is not considered a molecule because water has 2 hydrogens and 1 oxygen. It has 2 different atoms hooked together, hydrogen and oxygen. So, well, I'm sorry, let me clarify that. They are considered a molecule, but more specifically is considered a compound specifically. Just so you know though, a molecule is a group of atoms linked up together. So these 2 are considered just molecules, while this one's considered a compound specifically. It is a type of molecule, but it's more specific. It's 2 different atoms hooked up together. Alright, your book points out, as of 2012, there is 118 elements. So that's how many we have still currently. Now, some of them we've given exact names. So you'll notice in your periodic table, this periodic table is not, they've given this a little bit later on in your book. You'll notice that some of them, the ones down here, that they're given a 3-letter temporary name. We've given them their official names by this point. I can't show it because the camera's too far over, but they're given official names today. So the 3-letter names were the temporary ones, so they've had official names now. But your book's just pointing out that, okay, there's 118 elements, 88 of them occur naturally in the earth. The remaining 30 we can make in a laboratory with chemical reactions. We can basically force them together with their nucleuses and make a whole new type of atom from them. So the last 30 they are made in a laboratory, but you don't really find them out in nature. Alright, going back to this page. So compounds and molecules, making over that. A mixture, to make a note of that normally we find them as compounds or mixtures, physical combinations of elements and compounds. Typically we find them mixed up together as a mixture out in nature. So make a note for that one. We don't find typically just a block of gold all by itself. Like if you play Minecraft, you find whole chunks of diamonds or like diamonds or emeralds or quartz by itself buried in the rocks. So looking deep in the rocks to go find them. But you can find whole blocks of silver. Typically we don't find them like that where there's this giant chunk of gold. Yay! Typically you might find it in an impure version, like an ore, or you're gonna find it to where it's mixtured with other stuff. It's not just chilling out all together like that. An alloy is a metal mixture, so like we were saying that brass is a metal mixture, steel is a metal mixture, it's a combination of 2 different elements together. What was the other one? Bronze. Bronze is also a mixture. Well, it's an alloy because it's 2 different elements mixed together for it. So just make a note though, so alloys are metal mixtures, so just make a note for those. Alright, atomic symbols. So your book's pointing out that for the ancient chemists, in a lot of cases back in the ancient time periods, they would keep their alchemy or they would keep their recipes over what they were working with kind of a secret. So in some cases, they would try to make gold from lead. That was a real thing that people tried for a long time. So because of that, they would keep their formulas secret from each other because only they wanted to know how to make gold. By the chemists of the 17th and 16th centuries, though, they decided that this system was kind of confusing because each chemist or each alchemist would have its own basically symbols for things. Your book gives you a picture of, I think, 117, some of them. So some of the symbols you kind of recognize because some of these symbols we still use kind of for fun. So some of them you might recognize, oh, like the symbol for antimony, you might recognize, okay, that symbol looks kind of familiar for it. Mercury is another really common one. You might recognize Mercury's symbol. So because of that, you might recognize some of these from maybe video games or other places for it. But your book's pointing out, here's some chemical symbols from the alchemists to their present. Today, though, we give them letters to help represent them. So today, we use a chemical symbol for it. In 1813, scientists decided that using all the different pictures and symbols was too confusing, and they said, no, in order to spread knowledge, we want to use an easier system. So because of that, instead of using pictures or symbols, we want to use letters. It's easier and it's much more convenient. So each element is given a unique abbreviation or chemical symbol. It's either based on its common name or its Latin name. So some of them, they start with the first letter of their name. So like carbon starts with C. Yay, that makes sense and that's nice. Well, chlorine also starts with a C, so they can't call it C again, so it's Cl. So for chlorine. So just make a note though that some of their symbols are a little bit different, and that's the reason why. Your book points out Na, sodium. So if you look up sodium, Na, that its old name is natrium. So that's the old Latin name for it. So that's where its abbreviation comes from. So some of them are based off the old name, some of them are based off the current name. So most elements are given a 1-letter or a 2-letter symbol. It basically depends on which one was used first or which one's considered more important. Some of them you'll notice these ancient elements like water. No, water is not a pure element. Now, a lot of cases in video games or in TV shows, we'll talk about the element water. Okay, water is important, and they understood water is very, very, very important. But water is not made up of one element. It has the hydrogen atoms and the oxygen atoms in it. And so because of that, you don't find water on the periodic table. It's made up of the atoms of hydrogen and the atoms of oxygen. So this is a molecule or a compound specifically, but we don't have like an element for water today because it's made up of 2 or more. Well, water specifically is made up of 2 different types of atoms. Alright, you'll notice on the next page, your book has this long list of elements and chemical symbols. Alright, you need to memorize the ones in bold. So not all of them, not all 118, but you need to memorize about the 35 that are bolded. When I counted them, I counted about 35. So those are the ones you want to memorize. Some of them are going to be pretty easy. Some of them are not. So make sure you're working on it. The best way to do this is to use flashcards to help you memorize it. I don't know how well these show up on the screen. You might have to squint. You might have to see them. But like for W, you want to know the name of the element that has the W atomic symbol. That is tungsten. So make a note for that one. So chemical symbol, I said atomic symbol, I said chemical symbol. So tungsten, if you're looking for it on the chart, has a chemical symbol W for it. Because again, it's based off its old name. So the easiest way to do it is make flashcards. So since you're at home, I would highly recommend doing that. Next week, whenever you're in class with me, we'll do review games with them and help you memorize them. But the best way to do it is to just make flashcards for each one that you need to know, the bold ones, and then start drilling them that way. That's the best way to do this. It's the best and the easiest way to do this particular one. So for today and tomorrow, whenever we're drilling them, if you want to use your book to find them because you're practicing, you can, but you want to start learning them as best you can. You're going to have your quiz over next week over them. Probably either next Wednesday, Thursday, or Friday. I haven't decided yet, but make sure you are working on them so that way you're not caught off guard. Like for example, what is this one's name? So find it in your chart. So ZR, your book at least put them in alphabetical order. So ZR is zirconia. So make a note for that. Alright, what is B? So find B. So again, they're in alphabetical order. They'll be found boron as the name for this one. Alright, what's the symbol for chlorine? I said this one earlier. Find it in your chart. Chlorine has Cl. So chlorine, Cl. Alright, what has Cu as a symbol? Cu is copper. So good job. Hopefully you're finding these. This was a little bit harder. So Au. This one's based off the old name for it, so you're not going to find it at the front. So find Au. Did you find it yet? Alright, Au is gold. So Au is the atomic symbol for gold, based off the old name. He. I knew this one a lot today, so hopefully you recognize this one. Helium. Exactly right. Alright, I'm going to go ahead and stop there, but make sure you know them and you're starting drilling with them. I know it's kind of weird talking to a screen, but make sure that you're learning them because you want to start drilling them. Alright. Alright, your homework for tonight. Read pages 116 through 119. Answer on page 123, questions 1 through 3. So on page 123, questions 1 through 3. Start working on your periodic table though, start memorizing those bold elements. So don't forget, background paper, final draft is due Monday. I need 2 copies. So don't forget, 2 copies due Monday. Alright, you have a great day.